Hi everyone, my name is Sasha Olenev and I'm a lead embedded engineer at TechMaker. And today I'll be telling a small story about adventures of building a CAN bus sniffer. So a couple of words of who we are and what we do. TechMaker is a small community concentrated on embedded hardware. We are, first of all, hardware developers, as well as we try to share our knowledge, and we conduct offline teaching courses, trying to spread our knowledge and give some insights on how to write code, assemble hardware, pen test it, test the security, and do a lot of stuff. Also, in the meantime, it's kind of like our hobby, and we try to investigate a lot into security, both in web and in the hardware. And so a lot of people say we're some hackers in some way. Regarding the hardware, we have pretty long experience in developing different devices. And one would ask, why would you need another CAN bus sniffer? Well, first of all, the thing is connected with our main job. So me and Andrei, we both work for an automotive company called TIA. Its main product is its fleet management system that allows the user to remotely get telematics and different vehicle data from your personal car or from some kind of company fleet. And it also allows you to control it remotely. So in order to do that, a small piece of hardware is usually installed into the vehicle, and it allows to remotely send commands and inject some messages into the CAN bus. And because we needed to know how that whole thing works, we started investigating into that ourselves. Previously, we did not use our own hardware, but just took some ready-made GPS trackers and alarm systems, modified the firmware a little bit, and tried to work with the manufacturer in order to do the things that we wanted to do. And recently, we finally came to the understanding that in order to fulfill all our needs, we need to develop our own hardware. And basically, this is the story of how we came up with this whole idea. So in order to be able to remotely, for example, lock or unlock your car or start the engine remotely, you need to be able to understand what happens under the hood of your car, meaning all the electronic units in the vehicle are interconnected, usually with the CAN bus. And in order to know which frames does the ECU send to the different parts of the car so that it would start itself, you need to first understand what happens there, and you need to be able to reproduce the same messages in order to accomplish your task. So a lot of alarm systems or GPS trackers that already support it, they have spent a lot of man hours in order to reverse engineer the messages that go on the CAN bus. For example, one of our partners in their main office, they have an external elevator that they load the car into, take it to the 7th floor, completely disassemble it and strip it down, and reverse engineer it wire by wire in order to know which exactly messages to send where and in which order that should be happening. And so we were trying to reproduce the same thing in order to be used in our own hardware, and we needed our own custom tools in order to accomplish that task easier. Of course, you can buy some professional hardware that would be costing you thousands of dollars, and you can do that super easy. But we try to do it our own way with both reverse engineering and learning more and more stuff as we dig into this whole thing. And eventually, with this custom hardware, we were able not only to reverse engineer some cars we wanted to work with, but then we went to some car manufacturer bug bounty programs, and that was pretty much having fun trying to pen test and research the security aspect of injecting such messages into the CAN bus. And so if you're talking about the CAN bus sniffer, of course, there are tons and tons of already made projects on the internet, both open source or some commercial realizations. But the problem with most of them is that they're usually custom made, and one of the most popular dev boards is Arduino based. So usually people would take an Arduino Uno board or even Nano, attach a small transceiver so that you can access the actual CAN bus, and then it works. The problem with such approach is that it works for most of the people, but it doesn't work for us. The problem is not the high speed of the CAN bus. The problem is the percentage of the bus load that we usually experience. So by the standard of the CAN bus, the bus load is usually about 5 to 10% in the average car. However, if you're trying to investigate some security stuff, and for example, you need to tweak some parameters of the internal units of your car, you need to connect a special device called the dealer diagnostic kit. This is usually a super expensive piece of hardware that is manufactured by the car OEM. And there is a special computer with software that allows you to update the internals of the software of your vehicle, tweak some parameters, etc., etc. And basically, when you're trying to reproduce the same controls and tweaking with your own hardware, you run into a problem that you need to sniff and record what that dealership scanner is talking to the vehicle. But during that period, usually the bus load goes much higher to about 80, 90, or even 95%. And that's where most of the Arduino-based CAN bus sniffers fail. And that's how we came to the need to design our own device. Basically, additionally, we wanted to implement some custom scenarios in order to simplify the hacking process and reverse engineering. First of all, we wanted to be able to filter some frames. Of course, in modern vehicles, there are thousands of CAN bus frames per second. If you have the ability to filter them in the hardware and offload your main CPU and your code and your laptop, it would be much easier to investigate what's actually happening there. Also, we were trying a lot of modern cars in order to prevent for regular people that are not authorized to work with the cars to tweak some stuff. They can do some kind of authorization and authentication in order to be able to modify some parameters. And as we found out, a lot of those systems usually have kind of weak cryptography, and we are trying to hack and brute force the challenge response algorithms that would allow us to get authenticated and try to send some data. Also, this would allow us to either fuzz the system with some random CAN bus data or send our own customized frames. With recent vehicles, it became popular to use devices called security gateways, which is basically a piece of hardware that's monitoring the CAN bus activity. Usually it has multiple CAN buses connected to it. So modern vehicles can have up to 10 or even 15 CAN buses. And this is the device that basically supervises activity on all of them and filters what can be penetrated through the firewall. Usually this device is installed somewhere under the driving wheel, and it has basically, since it's a firewall, it basically separates your CAN bus network in two sides, the dirty side and the clean side. The clean side is where all the information, all the controls is going on, and the dirty side is the one that's accessible externally. For example, it can be accessed from the OBD port. Or this is also on the dirty side, usually the audio, video, and navigation systems are connected. And since they're they are able to connect to the internet if somehow by some vulnerability it will allow a hacker to remotely execute some code on it, and if it has the connection to the CAN bus, then your vehicle can be hacked in very many ways. So usually these devices try to filter the activity and not let the unauthorized and some malicious CAN frames to be penetrated from the dirty side to the clean side. And since we have been investigating such devices for a pretty long time, it has been essential to design a CAN bus sniffer that allows you to monitor multiple CAN buses simultaneously. For example, seeing what are you sending on the dirty side and monitoring if it penetrates through on the clean side, and et cetera, et cetera. So for the last 2 years, Bugcrowd has been conducting the car hacking bug bashes, which were offline events gathering car hackers from all around the world, trying to pen test and penetrate the security of one OEM manufacturer vehicle. And this has been going on for 2 years in a row. We have been there both times, and both times we found critical bugs. And last year we even get the best award, the best bug award. And so we went the whole journey, starting from the very first prototype, incrementally increasing the features and trying different stuff. For example, in order to understand how the CAN bus works, instead of getting into a real vehicle and breaking it right away, we assembled a CAN bus prototype and using ready tools, sniffed some frames from the real vehicle, then trying to replay them using our own table-based CAN bus, and testing our hardware incrementally using this small setup. Actually, doing your own device is a lot of fun. It's really useful to create your own tools, since in the process of making them, you understand the actual thing you're trying to investigate to much better. Hardware development is not that hard all the way, accounting for a whole bunch of cheap Chinese factories that allow you to cheaply manufacture the PCB. And after all, if you make your own tools, you understand them the best, and you can tweak them your own way so that they will suit your needs perfectly. Compared to multiple $1,000 tools that are usually come with fixed software, this is much more flexible. And actually creating your own hardware is a lot of fun. And in order to accomplish that, you need to go through multiple steps that will help you to get to the final point of having your own piece of hardware. First of all, you need to prototype your concept using some cheap do-it-yourself components. You can take the breadboard, some ready-made development boards, different components, assemble them together with wires, and just test your own concept, if that even works for you. Of course, you need to have a little bit of electrical engineering knowledge as well as programming, but that can be done using some free online courses now available at some platforms like Udemy, Coursera, edX, and lots of those. Then, when you have your concept ready, you would want to try to create your own printed circuit board. And that's where you need to start learning some PCB design software. As soon as you learn the basics of some PCB design software, it would be pretty easy to get your first board ready, because there are tons and tons of ready-made reference boards that are open source that you can check upon with and create something of your own a little bit customized. Then when you have the prototype in digital form ready, you just call the PCB warehouse, and then in really small amount of time, like a couple of weeks, they can ship you the ready PCBs or even the assembled PCBs. And then all you need to do is put in some kind of enclosure and then have fun developing the firmware and actually using the hardware. So that's pretty much how we started with our CAN bus sniffer. The first prototype looked kind of like this. This is not the actual prototype, but one of the revisions that we had. You can see here cheap Chinese development boards, a breadboard, some jumper wires, and some components that help you connect with. Then, after you tested this concept, you can try to make this thing more compact and assemble it and solder it together. And that's how we got the first version, which looked kind of more like a production device. As soon as you add some kind of enclosure, buttons, LEDs, and connectors to it. And then incrementally, we moved over and over, adding more features. At first, we used some ready-made development boards. Then we dumped them and went to using fully customized PCBs that has just the microcontroller on it. And this allows us to make the device even smaller, get more features into it, and tailor it as we want in order to fulfill our needs. As soon as you have the concept ready, you probably need to learn some PCB design. Nowadays, there are lots and lots of software like Altium Designer, which is a super powerful enterprise software, or you can go with some open source stuff like KiCad or EasyEDA or Autodesk Eagle. I personally prefer Autodesk Eagle. For me, it was the easiest to learn by just watching videos on YouTube. And recently, it has been acquired by Autodesk. Now it integrates with Fusion 360 and allows to do a full closed loop cycle of developing from the PCB to enclosure to printing it, the enclosure on 3D printer, and tailoring and adjusting this whole thing. As soon as you have watched some videos on YouTube, you can start actually designing the PCB. And every PCB starts with a schematic, right? So you need to think of which microcontroller, if this is a microcontroller-based project, first you need to pick a controller it would be pretty easy for you to develop for, right? We mostly use ST Microelectronics STM32 microcontrollers, which are probably the most massively spread right now. As soon as you have decided which way you want to go, you need to start to search for the components you will be using. So basically, you need to outline all the features you will want to have in your device and think of which components or which design blocks you would be using. There are tons and tons of reference designs already on the internet, both in the open source or in the data sheets and application notes of the manufacturers. So even if you don't know how to connect the certain part of the schematic, there are tons of reference designs from the manufacturers, or you can go to some open source hardware websites. Like one of the deal breakers for me to select actually Autodesk Eagle was that the SparkFun, which is a website with online store with lots of hobbies, Arduino modules and different hardware, they do provide all their boards as open source with the source file from Eagle. So for me, for my first PCBs, I went onto their website, searched for boards that were relevant to me, just download the files and learn from them. As soon as you have most of your schematic outlined, and you don't need to invent anything yourself. Most of the design blocks have already been built by someone else. You just need to search for it online and just interconnect them. Of course, this requires a little bit of electronics knowledge, but that's no hard deal. So as soon as you have the schematic ready, you need to start thinking how to transfer it to the actual hardware. First of all, you need to lay out all the components in order to space them properly, rotate and position in such a way that the traces would have the minimum length and you would have the minimum amount of traces going from one layer to another, and so and so. And this is a pretty complicated task, but if you approach it incrementally, it pretty fast unravels itself and becomes easy. So as soon as you have components kind of placed around the places you want to, You may also want to play with the microcontroller pinouts, since nowadays most of the microcontrollers have repurposable outputs and inputs. You may want different pins of the microcontroller may be able to handle the same function. And you might want to play with that as well in order to optimize component spacing and orientation. As you are doing the routing of the hardware, you need to keep in your mind a couple of principles that would simplify and improve the performance of your hardware. First of all, you need to properly design the power of supply of your system. Also, you need to avoid placing close to each other the analog signals and the high-speed digital ones, since they tend to add noise to the analog part. In order to reduce the crosstalk between different high-speed signals, you might also want to add some ground pooling and isolation between the traces. I usually place ground polygons on all the layers and allow it to fill all the space in between the signal traces. Another set of rules you need to comply with are provided by your manufacturing warehouse and is connected to the actual manufacturing of the PCBs. For example, you need to space the traces more than a minimum distance, or you can put two holes too close together to each other, or putting the trace too close to the edge of the board, and so and so and so. Most of the warehouses have them outlined in certain tables, and some even have the files that you can just, with the rules that you can just upload to your PCB design software, and it would automatically check all these rules. Of course, you also need to check if you have finished routing all the traces and all the connections you outlined in the schematic. And that basically sums up that process of designing the actual PCB. As soon as you're done with routing the board, you can proceed to ordering the PCB manufacturer. A lot of warehouses, and basically all of them, use a special format for accepting the board design called Gerber files. Every PCB design software can export your ready design into this format, and then you can upload it to any warehouse and they will accept it. Apart from that, a lot of warehouses allow you to just zip the board project and ship to them directly, and they will generate Gerbers for you and do the actual manufacturing. Nowadays, there are a lot of Chinese, American, and European warehouses that allow manufacturing small batches for really cheap prices. I personally prefer PCB way, and a lot of other warehouses allow you to order 10 pieces of your PCBs. If their size is smaller than 10 by 10 centimeters, the 10 PCBs will cost you something like $5. Also, right on their website, you can enter all the tolerances and manufacturing settings you want to. For example, the color of the solder mask, the color of the silk screen printing, and so and so and so. And after all, you get the calculator. You can see that usually for small batches, the PCB production costs less than the actual shipment. If you don't care about, if you're not super tight on timing, you can go with regular post. And for example, for $5 10 pieces batch, you will spend also like $9 for shipment. If you want to speed up the production and you need to get PCBs urgently, you can pay for some carriers like DHL, FedEx, or UPS and get the PCBs for shipped for like $30. But overall, the PCB production, if it's a small batch, usually takes 1 or 2 days and about a week for DHL to ship it to your country. So usually if you order the boards, for example, on the weekend, the next Monday, a week after, you can receive the ready PCB. So as soon as you have the boards ordered, you can go 2 ways for assembly. Either you can assemble them yourselves, and for first prototypes, it's kind of easy and fun. Usually I try to select simple components that are easy to solder, and then you would do the full cycle, right? So you receive the boards a week after. Meanwhile, you purchased all the components you needed, then you can solder them yourself, or you can find some local companies that would do soldering for you, or even individuals. If you need to speed up the production, the same warehouses that produce you the boards can do the assembly for you, and this is called PCBA, PCB assembly, right? And in order to do that, you need to generate more information for them. For example, you need the bill of materials and pick and place files. Bill of materials is basically a list of all the components that you need and possible replacements for them, because not always all the components are in stock in the factories that are there locally in China or in some other countries. So there are lots of replacement parts that can be substituted, and the design would, the PCB would not change, but the actual component that gets soldered can be different, right? As soon as you have the bill of materials ready, you also need to generate pick and place files, which are basically when the warehouses do the assembly, it goes on automated line and a special robot picks the component and places it many times per second on the PCB. And this is basically the file that generates your software that tells to take this component, rotate it into a certain angle, and place it at certain coordinate on the PCB. Of course, the ordered assembly increases the overall cost, but if you're ordering large batches of devices, this actually gets cheaper and cheaper the more PCBs you order. And right now, a lot of warehouses also have some discounts for assembly. For example, on the PCBWay, if you order over $30, that they give you the assembly for free. And lots of other warehouses have the same kind of discounts, and it has become pretty easy to accomplish. The last step that you want to do to make your device look kind of solid is create an enclosure for it. That would allow you for the device to be more production-like, right? So either you can use, and if you're fine with bare PCB, it's all good. If you have a prototype made on a breadboard like this, you can use a simple food container and place and screw it inside so that it is protected from mechanical impact, right? Other options is putting the PCB inside of a heat shrink tube, which does look kind of like an enclosure and allows you to quickly assemble or disassemble the device. Other than that, you can use some ready-made boxes, and there are lots available in the market of various sizes and various options of attaching the PCB to the actual enclosure. But keep in mind that you probably need to decide on the enclosure first and then design the actual PCB so that you would have all the cutouts that needs to fit inside this enclosure. Other way is to go with a custom-made enclosure that is a simple box with a cutout that you can design yourself right now, having lots of free software for 3D modeling. And then you can use some 3D printer to prototype the actual enclosure. And as soon as you have that, you can proceed to stuff like injection molding or other production grade like enclosures. And that would look like this. Also, you may want to print some kind of label with a pinout that would help you to know what happens inside the hardware in the future, and maybe some other functionality, put your logo, name, or something else. Hardware development is not that hard if you split it in smaller steps. And going from the prototype like this to this can actually take you a couple of weeks or even months, right? So usually, in order for the hardware design to be completed, I personally need 1 or 2 iterations of PCB design for fixing the mistakes I get in there. And well, in between these 2 sniffers, there are actually 6 generations of them. So this is version 6 and this is version 0. But this happened over multiple years since we're coming up with different features and designs we wanted and tasks we wanted to accomplish. And when we're talking about commercial development of the hardware, a whole bunch of different other aspects comes into first place, going from the testing of the devices with the support and of course security features. And tomorrow we will be hosting another 2-hour workshop where my colleague Ilya will talk about continuous integration and testing of the hardware development, and there you can get more information about that. Thank you for your attention, and I would be happy to answer any questions you have in the Hack in the Box Discord channel, or you can shoot us an email and we will be glad to help you.